This is the third narrated PowerPoint in the Case for Rhetoric series, applying rhetoric to science. And so what rhetoric of science does is it applies rhetorical theory to science. And in the reading for this module, there was made a mention of metaphor, which going back to the rhetorical canon is an aspect of style, and also a specific mention of Niels Bohr, who is a Danish physicist who was in on the early theories of the structure of the atom, and he actually continued with that and worked with developing atomic energy before, during, and after World War II. So we're going to look at some of that, some of my research specifically into these two aspects of rhetoric of science now. So what I'm going to talk about is the solar system analogy. And this was something that I ran into or started researching when I started my PhD program. And I was working on my first paper on metaphor in scientific and technical communication. And I was thinking to myself, what's a good example of scientific metaphor? And I thought, oh, an atom is a miniature solar system or something like that. Maybe I thought of the analogy first. I thought, okay, I'll use that. Now, how do I cite that? In other words, who came up with this first? And so I went back to some material that I had read back when I was working on my master's degree. And I wasn't really able to come up with anything like that, any source for this metaphor. I just bought a computer though, and it came with a copy of World Book Encyclopedia on a CD-ROM, so I looked up atom, and lo and behold, look what I found. Which to me said that the solar system analogy or metaphor was something that was in the realm of common knowledge, and so it didn't need to be documented, though I actually cited that to prove it in that first paper that I was working on. I kept wondering about it though, about what its history could be. And something that I did right after I finished my coursework for my PhD, I contacted a science education professor and told him I was looking for the presence of this analogy, and I wanted to know if he had any sample books that were used in public school teaching. And he did. He said these were all the major ones. And these 7 that you see here, these all use the solar system analogy or the metaphor for describing the structure of the atom. And looking here, you see a lot of familiar, well-known textbook companies, some of which have been absorbed by others, but all of these: Addison, Wesley, Harcourt, Brace, Jovanovich, Prentice Hall, Merrill, Reinhardt, Reinhardt and Winston, Houghton and Mifflin. These are all well-known publishing companies. So there were 4 that did not use the solar system analogy, and looking at these 4, you can see that all 4 of them were from the same publishing company, which to me hints at there being some sort of editorial bias, perhaps. Of the ones that didn't use the solar system analogy, they still used some sort of analogy. Feather said that the structure of an atom was like a cloud or like a beehive. Wistrom said that Bohr pictured the atoms as having a central nucleus with electrons revolving around it in well-defined paths. And let's see, McLaughlin said it was like a chocolate chip cookie. And then Frank said it was like a muffin with berries. And they also cited a Japanese physicist named Hantaro Nagioka, who said it was like the planet Saturn, having rings around it. That in itself became that ring metaphor became useful for Bohr, as we shall see. So, but anyway, that same science education professor, when I said I was looking for the solar system analogy, he said, "We know that's not really considered to be accurate now." And so, yes, I know, but it's commonly in use. And after I looked at these and told him about these others, he said, well, those are even less accurate." So, but and we'll get to why that is in just a few minutes. So, early atomic theory, we can go back to the ancient Greeks. Actually, Lucretius wasn't a Greek, he was an ancient Roman. He was getting a lot of his ideas, though, from Democritus, who was a contemporary of Plato and of Aristotle and those guys. And Plato did not like his work at all. He said that he thought all of his books should be burned. But Democritus was actually thought the universe consisted of many planets and many stars. So he was on to that very early on in the history of thought. A lot of people didn't agree with him at the time. The idea of the Earth being the center of the universe is sometimes referred to as an Aristotelian view. And that was true of Aristotle's physics. But Democritus also said that there were this idea of that we had of atoms moving into the void, and this was also to describe not only the atomic but also at the much larger scale of stars and planets. And we jump from there to René Descartes, who lived during the 17th century, which is when we think of the scientific revolution as having taken place. It has given us our modern science. It's when Isaac Newton lived, for example. We have actually Galileo at one end of the 17th century and Newton at the other end of the 17th century in terms of when they lived and were publishing. But it was still this, in terms of talking about atoms, Descartes in the 17th century is still talking about them moving through the void in these circulatory streams. And so when we get to these guys, we start to actually have a better understanding of that, and they tended to be classically educated, which meant that they learned Greek and Latin as part of their educational experiences, and so they may have been exposed to Democritus as well as Aristotle's physics. The first one, and they did, and these 6 individuals, I'm really thinking of them in terms of working together in 3 pairs. With Thomson and Maxwell, they had enjoyed kind of a student-mentor relationship, and you see those types of relationships with these, you tend to see them with these people. With Maxwell being the student. That wasn't true with J.J. Thomson and Oliver Lodge, though they were more contemporaries. And Lodge was the chair of the Department of Physics at the University of Liverpool, and J.J. Thomson ran the Cavendish Laboratory at Oxford University, which was certainly one of the most, or not Oxford, it was at Cambridge University. It was certainly one of the most prestigious science positions in the 19th century. And Ernest Rutherford came to work with Thomson at one point, J.J. Thomson. And then Niels Bohr also later came to work with Thomson, but while he was there, he met Rutherford and went off to work with him on the structure of the atom problem. So, look at these each a little more carefully. Thomson was, one thing that he's notable for, he was the first scientist to achieve peerage, which means he became an aristocrat. And the reason he was able to become an aristocrat in England was he made a lot of money from being a scientist. And the way that he made a lot of money was through various inventions that he came up with as he was involved with laying the first telegraph cable across the Atlantic from England to the United States. He actually went on board the ship, and so that was actually how he became wealthy. He also taught. Nobody ever gets rich doing that, right? He was exposed in his educational experience to this concept of Scottish natural philosophy. And Scottish natural philosophy is interesting because it's very much focused on the concrete. The Scottish natural philosophers don't sit around wondering if they really exist or not, or if a tree falls in the forest, whether or not it makes a sound. But they are very interested in analogies, and they think if you've got a new scientific idea, then you should be able to come up with an analogy in order to express it. If you can't do that, then you don't really have a firm understanding of it. And what Thomson was trying to do, where he came into wondering about the structure of the atom, is he was trying to figure out the nature of magnetism and electricity. What were they made out of? Certainly, it was, what was it? Is it just something we couldn't see it because it was just so very small? And that's where we get back to that idea of the ancient Greek atom. And the Greeks too were one way that they were interested in the atom, or one way they theorized that it did exist, is something that I call the bottle and the brick experiment. Some of you may have done this when you were kids. I did it, and to do the bottle and the brick experiment, what you need is a bottle and a brick. And what you do is you put the bottle down on the ground, preferably something hard like cement, and you take the brick and you drop it on the bottle, and it breaks, and you pick the brick up and you drop it again and again and again. As you do that, you see that it breaks up into ever smaller pieces, and the ancient Greeks were aware of this as well, that you could take something like, maybe they used something like maybe they used a brick in a pot. If you smash something, it breaks up into ever smaller and smaller pieces. So, well, anyway, that's what William Thomson, or Lord Kelvin, as he came to be known, when he became an aristocrat, was trying to figure out about the ancient Greek, about the atom, and he was working from the ancient Greek model. So the figure on the right, this is what Thomson thought that molecules looked like. They came in these various shapes, and this allowed them to be able to hook on to one another. And you can see there on the left that he's using, trying to figure out how they related, this idea of vibrations and so forth, and he's comparing them to stringed instruments and that sort of thing, bringing in the matter of tuning forks, which mixes his metaphor, but that's okay. That's something that we do in science. And then these molecules inside them, this is what he saw the atoms as looking like, as being created according to what he referred to as this vortex theory. Now, at this point, they weren't really theorizing a nucleus for the atom. That comes later. We'll get to that in a few minutes. But that's how Kelvin was theorizing the atom at this point, still working with the Greek model. Now, James Clerk Maxwell, he's best known for Maxwell's equations, which mathematically describe electricity and magnetism. And he was still working with the atom as something that was indivisible. But he started talking about molecules as these elastic spheres, and that becomes useful as we move towards the solar system analogy. You can see in this quotation that he is starting to use astronomical imagery, and he's trying to figure out why there's more of a difference in terms of how the moon affects the Earth during times of eclipses and during times of full moons and all that sort of thing. Especially if there's an eclipse of the full moon. He was thinking here about the tides and things like that. and it's kind of summed up there in the last sentence. So the streams of corpuscles, the Earth and Sun, are mere systems of atoms scattered in space, which present far more openings and obstacles to the rectilinear flight. And so this is important because he was seeing the Earth and the Sun as being systems of atoms. And what they were looking for here was unity between the atomic at the atomic level and at the astronomical. Now, J.J. Thomson he's principally known for the electron, and he was doing experiments with the cathode ray, which is basically a stream of electrons. And this is actually in old science fiction movies like Frankenstein and things like that, where they show the laboratory of the mad scientist. There's usually a tube with light running through it. That's a cathode ray. And this also has to occur in a vacuum tube. And these use of cathode rays, this was what eventually we began to use as radios and then televisions before the use of transistors. But even more recently, your computer screens, before we went to flat screens, was your CRT cathode ray tube. So it was still the same concept that was being used. But with the cathode ray, he was wondering, well, how could he had evidence that atoms were passing through a sheet of foil from the cathode ray. So how could something made of atoms pass through something else made of atoms? And his answer was the electron. So we see here, he's saying that the only case where he sees where something like this happening would be an analogy with the solar system. And with this type of attraction of other forces, of course, we know that that's gravity. And so there was some thought at that time, is that what's holding the atom together, since they now know that it is divisible, is the gravity. But as they came to discover the electron wasn't really bearing much of any charge, it couldn't work like that for very long, because then eventually it would just fall into the nucleus. So the nucleus had not yet been hypothesized. And here in 1907, we see him moving further towards using the solar system analogy to describe the structure of the atom. Now, Oliver Lodge was one of Thomson's colleagues, and one reason I include him is that he was very popular as a lecturer. Going to a public lecture on science was kind of a popular thing to do in the 19th century, and that was when women started to become more involved in science, because they were going with, that could be a date, believe it or not, would be going to a scientific lecture, and so that the fact that they were there set them to thinking about science as well. So Lodge also came up with this idea of atomic astronomy, which to describe the structure of the atom. And so you can see evidence of that here in this quote, which is from a book that he wrote in 1924 on this concept of atomic astronomy. Now, this one comes from a lecture that Lodge gave in 1902 to a group of electrical engineers, and you can see that he's drawing parallels between the atoms in Mercury and the planets in the solar system. And then here, from that same lecture, what he's doing is he's trying to explain what happens when two metals fuse. And the analogy he draws is it's similar to what happens when a comet enters the solar system. By 1907, even though, as I said, in the 1920s, for the general public, he was using the solar system analogy, by 1907 he was coming to question it himself, and that's because he was aware of what other physicists were writing about the structure of the atom, and you can see he lays out 5 possibilities, with the 5th one being the solar system analogy, but he is looking at other things like the possibility of electricity being what holds it together, and that was what was becoming a more popular belief at the time. Now, Ernest Rutherford, he went to the Cavendish laboratory to work with Thomson, and he was the first one of these scientists who grew up and was educated outside of the British Islands. He did have that type of cultural background since he was a New Zealander. And you can see here that in terms of his writing about the structure of the atom, this is actually what he is known for in terms of the structure of the atom. He is the one who first theorized the idea of a nucleus, and also that there was a good deal of space between these subatomic particles. And what's interesting here is that he doesn't use the solar system analogy, but you can still see remnants of it, like the use of the word orbit to describe the motion of the subatomic particles around the nucleus. And Niels Bohr was Danish, and he too came to Cambridge to work with Thomson, but he met Rutherford there and then went off with him to study the atom at Rutherford's lab in Manchester. And he is best known in terms of the structure of the atom. He's known for quite a bit of different ideas referring to atomic physics. But in terms of the structure of the atom, it's these 3 articles he wrote in 1913. And that's an interpretation by Victor Gamow, who was a physicist. And if this Bohr doesn't use the solar system analogy that a lot of times is attributed to him, and that problem was trying to deal with that 3rd bullet point on the right, the idea that what the electrons do to maintain their energy is they jump from orbit to orbit. And of course, planets don't do that. So this is the start of the breakdown of the solar system analogy, and with the beginning of describing the structure of the atom mathematically. Something we see Bohr doing in those 3 articles is shifting from using the term orbit to ring, though he used orbit in all 3 articles, but not nearly as often as he used the word ring to describe the path of the subatomic particles. So what happened to it? Partially it was cultural, as I was saying. That Scottish common sense philosophy maintained that if you add a new scientific theory, you need to be able to describe it with an analogy. And then secondly, of course, is that the quantum mechanics, it doesn't obey the classical model with those subatomic particles leaping from orbit to orbit. However, Bohr does specifically cite the solar system analogy in his 1922 Nobel lecture. And this was when he won the Nobel Prize for his work with understanding the structure of the atom. And so there you have it, the application of rhetoric to science. Questions? I'll see you online.